Hello everyone. Our topic today is regarding content-based recommendation. The goal of this unit is to provide you with an introduction of the content-based recommender systems and to discuss some approaches to generate content-based recommendations. Content-based recommender system can be used to make personalized recommendations to users by exploiting information about available item descriptions. In order to generate a recommendation, the question here is, which information do we need? First, we need some information about the available items. For instance, in the movie domain, we need some information describing a movie, such as genre or director. The second information is some sort of a user profile, describing the preference of the user or what the user likes. Main tasks of a content-based recommender system are to learn user preferences and to locate or to recommend items that are similar to the items the user liked in the past. Most content-based recommendation techniques focus on recommending items with textual content, such as a web page, newsgroup messages, books, or documents. The content of items can be represented in two forms, unstructured and structured. For the unstructured form, the basic characteristics of items are described by free text descriptions. For the structured form, each item is described by the same set of attributes. For instance, in the table shown here, you can see how to represent books in the structured form. So we have each row of the table represents the content of a book. Each book is described by a set of 6 attributes: title, genre, author, type, price, and keywords. So in the next slides, we will discuss some common approaches to generate content-based recommendations. So in this unit, we will go through 4 approaches. The first approach is Dice coefficient, measuring the similarity between the user profile and item description. The second approach is TF-IDF, term frequency inverse document frequency, measuring how important a word is in a document. The third approach is a relevant feedback, using the feedback of users to improve the qualities of recommendations. And the final approach is probabilities method, estimating the conditional probabilities of an item A being bought, given that a customer has already purchased item B. First, we discussed one of the simplest approaches to generate recommendations in the content-based recommender system. This approach computes the similarity between an unseen item and the user profile based on the category overlap. So this is a formula to calculate the similarity. So in the upper part of the formula, we multiply 2 by the overlap categories between the user profile and the item description. The bottom part of the formula is the sum of the numbers of categories of the user profile and the number of categories of the item representation. Let's take a look at an example in the software engineering domain. So we assume that we have a set of software engineering related learning units. Each learning unit is characterized by a set of 4 categories. So as you can see on the screen, we have 4 different categories, such as Java, UML, management, and quality. So, for instance, in the learning unit L1, we can see is this learning unit is assigned to 2 categories that are Java and UML. Assume a user UA has already consumed the items L4, L6, and L10. The last row of the table shows the profile of the user UA. So now we can calculate the similarity between the user profile and each of not consumed item using this formula. Let's take a look at the learning unit L1. So the similarity between the user profile and this unit is calculated as follows. So the numbers of overlap category between the user profile and this unit is 1. Therefore, in the upper part, we multiply 2 by 1, then we get 2. In the bottom part, we sum the numbers of the categories of the user profile and numbers of category of the learning unit L1. Then we have 3 plus 2, and we get 5. Consequently, we have the similarity between the user UA and learning unit L1 is 2 divided by 5. Similarly, we can calculate the similarity between the user UA and each of other learning units as shown on the table. So we can observe that the learning unit L8 is the most similar item to the preferences of the user UA, and therefore it is the best recommendation candidate for the user. Next, we will discuss another method to model items. It is called vector space model, which extract keywords from the item description and calculate the weight or the importance of keywords using the TF-IDF weight. So before going in detail of this approach, we need to know why do we use this approach. So the reason is that the simple keyword representation of a document can trigger some issue, particularly when keywords are automatically extracted. Not every word has similar importance. Actually, some keywords should have a higher importance compared to others. Another issue is related to the length of the documents. The long documents have a higher chance to have an overlap with the user profile in comparison with short documents. In order to measure the importance or the weight of a keyword in a document, we use TF-IDF technique. TF-IDF stands for Term Frequency Inverse Document Frequency. This technique is usually used for information retrieval and text mining, which reflects how important a word is for a document. This approach provides an important data for search and helps to figure out which terms are the most important, most relevant for a document. There are 2 parts. The first part is TF, term frequency, measuring how often a term appears in a document. The second part is IDF, inverse document frequency, aiming to reduce the weight of terms that appear in all documents. The main idea of IDF is if a term appears more often in other documents, then this term will be less important. So in this slide, I will show you how to calculate the weight of a term in a document. Given a keyword I in a document J, we have TF-ij represents the term frequency of the keyword I in the document J. This value is usually normalized to prevent bias towards long documents. In a long document, a keyword usually has a higher term count regardless of the actual importance of the term in the document. So TF-ij is the ratio between a TF value and the maximum frequency within the document. The IDF of the keyword I is the logarithm of the number of all recommendable documents and the number of documents in which the keyword I appears. So finally, the TF-IDF is the multiple of the TF and the IDF. Now let's take a look at an example of the TF-IDF representation. Each document is a count vector with n dimensions. So in this table, each document is represented in a column showing a vectors of 7 dimensions. This means each document is described by 7 different keywords. And here is the representation of TF-IDF. Each document is now represented by a real value vectors of TF-IDF weights. Next, I'm gonna show you an example of how to calculate TF-IDF weights. Given a document D with the term A, B, and C, the frequency of term A, B, and C are 3, 2, and 1 respectively. Assume the document D belongs to a collection of 1000 documents. So the total term frequency of term A, B, and C are 50, 120, and 98 respectively. Now we calculate the TF and IDF for each term as follows. So the TF of term A is the frequency of term A divided by the maximum frequency. That means 3 divided by 3. So the TF of term A is 1. And the IDF of term A is the logarithm of 1000 divided by 50, then we got 1.3. Consequently, we have TF-IDF of term A is the multiple of TF and IDF of term A, and we get 1.3. Similarly, we can calculate the TF-IDF of terms B and C as shown on the slide. So in this example, we can see term A has the highest weight. That means term A is the most important term in the document D. Next, we will discuss some solution to improve the vector space model. So vector space model usually triggers some disadvantages. Vectors representing documents are usually very long and sparse. Therefore, before the vector space model can be used to proceed any query, all documents must be pre-processed. So we should remove stopwords or articles out of the documents. These keywords appear very frequently in every document, but they do not have a lot of informational content. And that's why we need to filter them out of the corpus. We can also use lemmatization to replace variants of words with their common lemma. For instance, we can replace went with go or is with be. We can also use side cutoff, which means we do not use all words, instead only using top and the most representative words in the document in order to remove noise. Additionally, we can use lexical knowledge or more elaborate methods for feature selection and remove irrelevant words in the document. TF-IDF approach has not taken into account the relation between terms. Therefore, some methods regarding lexical relations can be applied to discover the relations among terms in the document for the purpose of improving the vector space model. Besides, some n-gram model can be used in order to combine multiple words, because these combined words can bring more descriptive information compared to single words. For instance, a topical anagram model can be used to model topics from documents. Topical anagram model is able to decide whether a bigram is a phrase or not according to the context. For instance, in the camera domain, the bigram good picture is detected to carry a special meaning, which is really related to the camera topic, whereas the bigram good news do not relate to the camera topic. Next, I'm gonna present another approach of content-based recommendation, so-called relevant feedback method. Retrieval quality strongly depends on the capability of users to formulate query with right keywords. Depending on how the query is formulated by the user, the query can result in relevant or irrelevant documents. In order to increase the numbers of relevant documents, relevant feedback method should be used. This method allows the user to give feedback for retrieval documents, and then the system learns a prototype of relevant or irrelevant documents. Thereafter, queries are automatically extended with additional terms of relevant documents. Based on the modified query, the system shows revised result to the user. This is an example system of relevance method. In this system, a user is searching for instance, a bike. So he enters the keyword bike, and the system returns a list of bikes. This system supports some functionality to get feedback from the user. For instance, the search functionality allows the user to select preferred items. Then the list of referred items is sent to the system. Based on that, the system can filter more relevant results to the users. So the search activity can be repeated by the user until the more appropriate items are found. Next, I'm gonna discuss with you the another approach called Rock-Hill method. This is the standard algorithm for the relevant feedback method. The main idea of this algorithm is to find a query vector that maximizes the similarity with relevant documents and minimize the similarity with non-relevant document. This figure obviously shows the idea of Rock-Hill algorithm. So in this figure, cross size stand for non-relevant documents and circle size stand for relevant documents. So we can see that the initial query returns a document which is quite closer to irrelevant documents. This method tries to find a modified query vector that helps to return documents which are much closer to relevant documents. The modified query vectors of an original query vectors is identified using the following formula. So in this formula, we have alpha is the weight of the original query vector, beta is the weight of positive feedback, and gamma is the weight of negative feedback. We have D plus is the set of relevant document vectors, and D minus indicates the set of non-relevant document vectors. In this algorithm, normally only positive feedback is taken into account because it is more valuable than negative feedback. Finally, we discussed the probabilities methods. So as you might know, recommendations are also considered as a classification problem which has a long history of using probabilities methods. For probabilities method, the main idea is to determine whether a document belongs to a given class. For instance, hot or cold, buy or not buy, in the scenario where the user is searching for items and the system has to predict the probabilities of a specific item to be bought by the user. Let's take an example. Let's take a look at this example showing 6 documents. So each document is represented in the form of a Boolean representation, where 1 indicates hot class and 0 indicate cold class. Now we calculate the conditional probabilities of the document A hot based on the Bayes theorem. So we are going to calculate the probabilities of the document number 6 to be in the hot class. In order to calculate this probability, we have to consider the probability of each attribute of the document under the condition of the label equal to 1. That means we have to calculate the conditional probability when recommender equal to 1 under the condition of the label equal to 1, and so on. So the probability of the first attribute when the recommender equal to 1 under the condition of the label equal to 1 is 3 divided by 3. For the second attribute, intelligent equal to 1, under the condition of the label equal to 1, we have 2 divided by 3. For the next attribute, learning equal to 0, under the condition of the label equal to 1, is 1 divided by 3. Final attribute, school, the probabilities when the school equal to 0 under the condition of the label equal to 0 is 2 divided by 3. So by multiplying those values, we have the probability of the document number 6 belong to the hot class is 0.149. Okay, so in this unit, we have already gone through some basics about content-based recommender system, Content-based recommended system generate a personalized recommendation based on the description of item and user profile. This approach has two advantages. First, content-based recommended systems do not require the user community, and therefore it helps to resolve the co-star problem. Indeed, compared to collaborating filtering recommended system, the content-based recommended system do not need to collect the preference of the user for an item, as well as the ratings of other existing user in the system. If you still remember, in the collaborating filtering recommended system, the system has to find the nearest neighbor of the user and then recommend to the user's items which are liked by the nearest neighbor. And this faces a co-star problem when a user first comes to the system or when the information regarding the preferences of the user community is not available or very sparse. However, this approach shows some disadvantages. So the main approach of content-based recommended system is to analyze keywords from the item representation and user profile to find the similarity. However, keywords alone are not sufficient to judge the relevant item. The reason lies in the up-to-dateness of the keywords or lie in the writing style of the document. Sometimes the content is too short to extract useful information. Besides, some contents may not be automatically extractable, such as multimedia items like songs or movies. Another limitation is related to the diversity of recommended items. So the main idea of the content-based approach is to recommend items that are liked by the user in the past. Therefore, most of the case, items recommended to the users is too much similar. But in reality, in some cases, users want to experience something new. For instance, in the tourism domain, users might expect to explore new places that are quite different from places that he or she ever been. So that is all about our unit. Thank you very much for your listening.